Lesson number 9, sinusoidal functions. So all of these graphs that we've been looking at, these sine and these cosine graphs, are called sinusoidal functions. Periodic phenomenon have sinusoidal graphs. The time of sunrise is a function of the day of the year. If I mapped it out over 3 or 4 years, you'd start to see this up and down pattern as you go through times of the year. Sunrise is earlier in the summer, later in the winter, and you get that repetitive pattern. The height of the chair at a Ferris wheel. It starts off low, it goes up to the top, comes back down, goes up to the top, comes back down. You get that sinusoidal function. The depth of the ocean due to the changing tides. If you go down east to the Bay of Fundy, the water comes in the evening, and then it'll actually go out during the day. And again, the depth of the water becomes this sinusoidal function. The Panama Canal is the same thing. The water comes in and it comes out at different times of the day. So because that is a shipping route, the ships have to know coming in and coming out when are the safe points of the day. Otherwise, they're going to get grounded or they're going to get stuck. Most of the equations will be a function of time, and the variable used will be t. Because it's a function of time, we have to read the questions carefully because sometimes our rounding rules are not going to necessarily work. We're not always going to round to the closest. We might have to round up or down depending on the situation. So if we look at class example number 1, it is the water in a harbor. So the depth of water in a harbor T hours after midnight can be approximated by the following function. D of t equals 12 plus 5 cos 0.5 t, where t is between 0 and 24 hours. So question A asks us to determine the minimum and the maximum values. So from the last section, how did we calculate the maximum values of the function? How do we find max? D plus A. So in this function, what's the value of D? 12, even though it's written at the front. And what's A? So the maximum is 17 meters. And then how do I calculate the minimum? D minus A. Okay. So I get 12 minus 5, which would be 7. So the water is going to range anywhere from 7 meters at its lowest point to 17 meters at its deepest point. Question B asks us to determine the period of the function. So how do we calculate the period? Remember how we calculated the period? 2 pi over b. And in this equation, what is the value of b? So 2 pi divided by 0.5, which is the same as divided by half. So what's 2 divided by 1/2? 4. So I would get 4 pi hours. Okay, question C says write a suitable window that could be used to display the graph of the function. So in this graph, my x-axis is my time. And I'm actually given the time range. What is my time range? 0 to 24. Okay. And what is a suitable scale? What can I go up by? 2's? Okay. And then my depth. What do I know about my maximum depth?
17 meters.
17. So what would be a suitable range? So it's a suitable window, not ranges. So what I want to be able to see on the screen, what should I start at?
You could start at 0.
Yeah. And then go up to what?
Maybe like
then what could I go up by?
2's again.
Sure. Okay, so let's graph that. What mode should I be in? Radian mode, good. So start with my window settings, 0 to 24, going by 2's, 0 to 20, going by 2's, and then I go into my Y editor, and I get 12 plus 5 cos 0.5x. Does this look like a sinusoidal function? Yeah, so I get this waved pattern.
This one is always excluded.
So if I sketch this, I get this sketch that kind of looks like this. I think it came back down because we were at, fix that. Would be my 17. Sorry, this would be my 24. There. So the question is, what is the depth of the water to the nearest tenth of a meter at 2 a.m.? So how would I determine the depth at 2 in the morning?
T equal 2.
Let T equal 2. And then what would I do? Could I use the calculator? Could I use the graph? And how would I use the graph to find that?
You can go to your table of values.
I could go to my table of values. I could also press trace and 2. And what do I get to the nearest tenth?
14.7.
14.7. There's a ship that requires at least 8.5 meters of water in the harbor, a ship that requires a minimum of 18.5 meters of water is in the harbor at midnight. By what time to the nearest minute must it leave to prevent grounding? So remember, my max is at 17, 8.5 is going to be here. So what intersection point do I want to find? Do I want to find the first one, the second one? What do we assume?
You find the first one.
So let's find the first intersection. So we let y2 equal 8.5, and we find the intersection. I'll give you a moment to do that. I need to fix this graph because I just realized I don't have enough cycles in the 24 hours. So what's my intersection point? When you're finding these intersections, this line up here tells me which graph I'm on. So I'm on the coast graph. If I press the up down, it'll bring me to the next next graph, so then I can scroll straight over instead of having to go, instead of having to go up and down. .6923, okay? So this is 4.6923876 hours after midnight. So I get the 4 a.m., but how do I convert this part to a time that we can recognize? Times it by 60. Do you remember how to pull that number to your screen so you don't have to type it all in? If I quit and I type the X, it'll bring that number for me. And then I can subtract by 4 and then multiply the remaining by 60. And I get 41.54 minutes. Now remember what I said at the beginning of this section, we have to really be paying attention to our rounding rules, because the rounding rules with time do not always follow what we think they should follow. So if this is me at midnight and I have to leave before this time, am I leaving at 41 minutes or at 42? 41, because at 42, I'm slightly past. At 42 minutes, the water level will be slightly less by 8.5. In reality, I probably wouldn't cut it that close, but if I had to, I would have to leave at 4:41, not 4:42. And then the next question is, when can they return back? So that would be the second intersection point, this one. So find that second intersection point. And tell me what you get when you've got that one. So what did you get for the intersection, Evan?
I got x equals 7.873.
Okay, so now I know I'm at 7 a.m. I take that 0.873983 multiplied by 60. What do I get?
52.43.
Okay, so again, think about this. This is at 7 o'clock in the morning, 7:51, 7:52, 7:53. So do I round this to 7:52 or do I round it to 7:53? Has to be 7:53. Because again, at 7:52, I'm actually still below that 8.5. Okay? Okay, class example number 2. Go. In a certain town in Alberta, the time of sunrise for any day can be found using the following formula. T equals negative 1.79 sine times 2 pi times d minus 78 all over 365 plus 6.3. T is the time in hours after midnight, and d is the number of the day in the year. So question A says, write a suitable window that can be used to display the graph of the function. So D is the day of the year. So what would be a suitable range for the day of the year? How many days are there in a year? So my suitable window range could go from day 0 up to day 365. What should I go up by? Doesn't have to be anything exact. It doesn't have to be a multiple of 365.
Maybe like 50s.
Sure. So then each tick mark would represent 50 days. Something just so that I can get some kind of ability to kind of see where I am on the graph. Okay? Now T is the time. So remember, I can use my D value and my A value to help me find the min and the max, which can help me find some suitable time ranges. So if I add them together, D plus A, I would get 4.51. And if I subtracted them, 6.3 minus negative 1.79, I would get 8.09. Which means in this particular Alberta town, sunrise varies from just about 5 o'clock in the morning to just about 8 o'clock in the morning. So if I wanted to put this into a window setting, I could start at 0 and go up to, sure. And what could I go up by? Choose. So every tick mark would represent 2 hours. Okay. Question B says, use the formula to determine to the nearest minute when the sun rose on May 7th, which is the 127th day of the year. So it would be negative 1.79 sine bracket 2 pi bracket 127 minus 78 divided by 365, and then another bracket plus 6.3. So I get 4.96292. So 96292. Take that 0.96292 and multiply it by 60. And what do I get?
57.77.
Okay. In this case, would I round down to 57 or would I round it up to 58? Will the sun begin to rise at 57? No, so I have to bring this up to 58. So the sun rises at 4:58 a.m. Question C says determine on which days of the year the sun rose at 7 a.m. So how would I do that one?
Make T equal to 7.
Okay, do I want to solve this algebraically or do I want to try to solve it graphically?
Graphically, because I tried it.
Solve it graphically, it'll be a lot easier because otherwise then you're having to do sine inverse and such. So you put this in for y1 and then let y2 equal 7. How many intersection points are you going to get? How many times of the year will the sun rise at 7? Okay, so here's my graph that comes up, and you'll notice that the sun will rise at 7 o'clock in the morning 2 days of the year. So what are those days? So what do I get for unrounded numbers? I get day down to? Day 54 or day 55? Which one's going to be closer to 7 a.m.? 54 or 55 if I'm supposed to be at 54.6? Day 55 is going to be closer to 7 a.m.
That's what I said, and I was like, oh, I guess I said
Okay,
it
what
wrong.
about at 283? Is it 280, the 283rd day or the 84th day? The 84th day. Okay, so the questions for you to practice are 1, 3, 6, and 7.